So we talked about exothermic, endothermic. So quick recap of last lesson, which is crucial for what we're going to do today, is the idea that every single chemical reaction has got bond breaking and bond formation. Okay, so every single chemical reaction. So bond breaking is at the reactant side, and in order for bonds to be broken, energy needs to be absorbed. On the right hand side of the equation is the formation of product, where energy is released as the bond forms. Now both is happening in every single chemical reaction. So how do we then classify a reaction as exo or endo overall? Overall, they are classified based on which side is greater. Okay, so the side that with a greater requirement of energy, if you are releasing more than you're absorbing, then you are exothermic overall. If you are absorbing more than what you release, then you're an endothermic in nature. So we talked about that, how an endothermic reaction causes cooling down of the surrounding, which can be measured using a thermometer, and thermometer will show a drop in the reading. Whereas an exothermic will do the exact opposite, and exothermic will be causing an increase in the overall temperature. So that's the idea. Now this delta H, that takes us to the next thing, which is the symbol of delta H. I'll write it up here. So delta H. Now whenever you see this delta H, that stands for enthalpy change. Alright, so enthalpy change. So enthalpy is energy of a bond that is either being made or being broken. So we can call it simply energy change. Now, when we say an enthalpy change of a chemical reaction, it means energy that will change from the process of breaking the reactant to the process of forming the product. So enthalpy can be represented here. You would see that it says enthalpy is negative. They put here delta H equals to negative. Delta H is equals to positive. What does that mean? This is not mathematical. Energy cannot be, it cannot be negative. Mathematically, energy cannot be destroyed because law of thermodynamics says energy changes form, but energy cannot be destroyed. So technically, negative value in mathematics means something that doesn't exist, right? So if you have a negative amount of money, that means it's money that you don't have. But here, negative works as a symbol. So if I give you a delta H, if I say a delta H equals to negative 30 kilojoule, what does that mean? It means that this reaction, two information I get from this. One, the negative symbol tells me that this is an exothermic reaction. And the second information, which is the value, tells me that the bond formation releases 30 kilojoule of energy more than the bond breaking part. That's what it says. So you know that energy is being absorbed before, so you have got A plus B giving us C plus D, for instance. So this section here, which is the bond breaking, this section here is the bond formation. If this enthalpy value is given for this reaction, it simply means whatever this amount that came out here, which we don't know, there's no way for us to tell just using this information. But all we know is this area here, which is the bond formation, has released 30 kilojoule more than this side. So I guess you can work it out. If I say A plus B, right, this area has absorbed 100 kilojoule, can you tell me how much C plus D is released? 130, correct. So if you can figure that out, you understand what the meaning of enthalpy change is. So that's the two information. The symbol, negative symbol, tells us that this is exothermic. And this is the amount that is the change. Because the idea is you're absorbing and you're releasing. How if I change this to positive? Positive can be two ways. One, they give you the positive symbol, or they don't have anything there. If there's no negative sign, then by default it's positive. So what is the meaning if it's positive? If it is positive, then it is known to be endothermic. Endothermic. And what does the value represent? The value represents that endothermic, which means it's overall absorbing. In this case, if I say this is a positive 30 kilojoule, that means if this is 100, then this side should be 70. Yes. Alright, that's energy change. So we'll talk more about energy change shortly. Now we're going to talk about activation energy. Now activation energy is a simple concept. I'm not going to go too deep in it now because it's something that we'll talk about in our next chapter, rate of reaction. We'll talk about activation energy in detail. But now just putting the concept of activation energy as simple as this. Now for reactions to happen, particles need to collide. So like, imagine this again. I put A and B in a beaker. The idea is A and B needs to collide in order to make C and D, in order to make that product. Correct? Now, the law for kinetic theory of particles demands simple things, such as when two particles collide, they must meet a certain amount of energy. There is a minimum set energy to become product. Okay, there's a minimum set energy. So let's assume, right? So I've got A and B. So I've got particle A colliding with particle B. Now, this is just one particle that I've drawn. In a beaker, there should be thousands of particles, right? So these two collide. Now, there's two outcomes from this collision. One, they collide and they form the product, ND. Or they just bounce off back to their way. Just bounce off back. Now that's the two outcomes. Now what decides which is the outcome? Is the amount of energy the particles will possess. Naturally. We call that as kinetic energy, right? That energy. How much energy does this particle collide? Now let's set the rule for this reaction, the activation energy as 100 kilojoule. Right? Let's decide that it's 100 kilojoule per mole. And let's say A is going to collide with B. A came with 50 kilojoule. And B came with 30 kilojoule. Now they collide. What is the total amount of energy we get? 80. Is it enough to achieve 100? No. That's when they bounce off. We call that as unsuccessful collision. A collision that didn't bring about a change. A collision that didn't bring about a chemical reaction. No reaction. So then the particle bounce off, they're randomly bouncing off, right? They will collide more and more with every particle that's around them until suddenly this is bouncing with another B that is 60 kilojoule. Now how much total? 110. 110, right? Now this will become product. Because you have met, here is when it does not meet the minimum energy. Now that's the idea. So for now, I only need you to hold the thought that activation energy is the minimum energy needed for particles to become product. We will go into the details of activation energy later in the next chapter. For now, you just need to hold that idea. So every single chemical reaction on this planet has got its own activation energy. Now let me ask you a simple thing. You know this. You remember putting sodium inside the water? No. What happened? Immediately exploded, right? Then that sodium is a metal. Now if you have, I give you a small piece of iron block. When you drop it into the water, will it react?
No.
Technically it will. Because iron will rust, right? But it doesn't happen so fast. It takes a long time. Some things naturally have very low activation energy, so making the reaction possible immediately and instantly, like that block of sodium inside the water. Some substances takes a long time, like that piece of paper you have in front of you. Can it turn into carbon?
No.
It can, but not on its own. Can it? Is this piece of tissue here? Is this reacting with the oxygen?
Yeah.
Can it? The question is, can it react with the oxygen? The answer is yes. But is it reacting with oxygen? No. It doesn't, because the activation energy is high. So I need to help it. That's when I burn it. I bring fire. So by bringing fire to the tissue, what happens? The tissue gains enough energy in order to react, and it will convert itself into carbon. Okay? So that's the idea. That's the concept of activation energy. We supply enough energy in order to make the reaction possible. Hey, congratulations, Audrey. Okay, alright. So now let's go more beyond the activation energy. So for now, just need to know activation energy is the energy needed for a reaction to take place. If they don't meet the energy, then the reaction doesn't naturally take place. Okay? So we'll talk more about activation energy later. So now let's move into the next part. The next part is simple. It's just some examples. It's good to know examples. How does this help? This helps in your multiple choice question, which tend to come out. It's quite common. They come out, you need to answer, you need to pick which one is exo, which one is endo. So you've got some common ones. Next week is break. After break, when you come back, the double period will be a lab session. In the lab session, I'll get you to do some of this common reaction. For example, like this dissolving acid. I'll let you try dissolving acid and then feeling it in your hand whether it's hot or is it cold. There's a bunch of chemical reaction that you can do. You'll measure using thermometer. You will also touch with your hand and feel whether it's endo or exo. So we'll do this when you come back from your break. So some of the common things. Remember, I want you to remember, combustion is very common in exam. Combustion of anything is always exothermic. The word combustion there is exothermic. Okay? Now, I want you to know the difference between combustion and thermal decomposition. It's two different things. Combustion is when something is being burned directly. That object becomes the fuel. I hold this over the bunsen and this burns. That's combustion. But if I put this inside a beaker and then heat the beaker, which means I am not putting this into the fire as a fuel, but I'm subjecting this to heat and hoping that it will break down on its own. That will be thermal decomposition.
Is it all including oxygen, right?
Yes, correct. Combustion will lead to substance combining with oxygen to form a new product, like carbon becoming carbon dioxide. Thermal decomposition is taking a compound and breaking it into its constituents. Like if I take ammonium nitrate, for instance, I heat it up, get it to break down to release oxygen or nitrogen dioxide gas. That's thermal decomposition. So thermal decomposition will be an endothermic process because it absorbs heat in order to break down. So this is common. Combustion is common in exam. Neutralization is common in exam. Respiration is common in exam. Okay? So these are common. Combustion, respiration, and neutralization is common. Condensation, freezing, I don't think you need to take an effort to memorize it because you know this, whatever process that needs to overcome if you're overcoming the force of attraction, then it's endo. If it's forming the force of attraction, then it has to lose energy, so it's exo. Okay, so comes the endo again. So common photosynthesis also quite popularly found in multiple choice questions. They like to give you, either they give you 3 endo and 1 exo and ask you which one is exo, or they do the opposite. Right? So this one is quite common, so I want you to remember this. And thermal decomposition. Please make an effort. This one is the most popular wrong answer from the students. They always somehow pick thermal decomposition as exo. Because they always, in their mind, they compare it with combustion, burning something. Thermal decomposition is not. Thermal decomposition, we want that substance to absorb the heat in order to break down. So the action of absorbing the heat makes it endothermic. Okay, so of course, reaction of sodium hydrogen carbonate with dilute acid. This one is something that you will do in the lab with me. Then you will remember it better to be as endothermic reaction. The rest, of course, overcoming forces of attraction. Evaporation, boiling, melting. When you overcome forces of attraction, that becomes a physical process. Yeah, so this one is something that you guys need to take an effort to try to remember. Okay, alright. So let's go on to this. Now, this is the formula that you will find in your book on how to calculate enthalpy change. Total energy of product minus total energy of reactants. I'm going to propose a different formula. Now I'll try to justify why, okay? Alright? So I need an example, so I'll use an example here. So we'll use this example again, right? So let's say A plus B, C and D. Wait, let me move this a little bit. Let me change this to an actual reaction. Let's do an actual reaction. So CH4 plus O2, CO2, H2O, and you have 2 and 2. Okay, so let's use this formula, yeah? Okay? I want you all to do this calculation for me. Very simple. The sum of energy, this one is important. You see here, delta H, total energy of product, minus total energy of reactant. What do they mean? It's like this, yeah? Let me explain the brief version, then I'll explain the extended version. Now the brief version is simple. I total the energy. What's happening to energy here, this side, on the left side?
Bond breaking.
And what's happening to the energy? Is it being absorbed or released? Absorbed, very good. Okay, so energy is being absorbed. Let's just say, I just give you, here we are absorbing a total of 100 kilojoule per mole. Right? So when I say 100 kilojoule per mole, that's a unit. Now, this is the total energy being absorbed. So what is those energy being absorbed? It's being absorbed to break the bonds between these particles. I'll talk about the bond in detail shortly. Now here, total energy that is being released as a result of the bond formation here is 150 kilojoule per mole. Now, of course comes the question, why is the value different? Isn't it all the same atoms? The atoms before and after is the same. Of course they are arranged differently, but why the value is different? Anyone? Any idea? Why is the value different?
Can you repeat the question?
Okay, like, see, I've got carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. All the same atoms, right, before and after? Of course they are rearranged. No. The question is why is 100 here, 150 there? Like, why would the energy becomes different?
Energy is released when bonds are formed.
That's not the answer.
Also the surroundings or something.
Not really, not.
They're writing with different
Different what?
arrangement.
Okay, that's the closest to the actual answer, okay? Close enough. The answer is because every bond has got a different energy within its bond itself, meaning it's like this. So here, what is the bond that we're talking about here? So I'll take this one out. So here, let's talk about the methane first, right? So the methane is this. This is a methane, because you don't know it yet. Eventually you will. So this is methane. So what are the bonds that exist in a methane? There's a carbon to hydrogen single covalent bond, correct? Now that bond has got a certain amount of energy in it. You don't have to memorize. These energies are usually given in exam, which I'll show you after this. They are always given and you just need to know what to do with them. So carbon to hydrogen, for instance, I'll just say carbon to hydrogen. Maybe the value is 450 kilojoule. That's a value fixed. And that value is the value of the carbon to hydrogen bond. Which means if I want to break that bond, if I want to chop this bond, right? I want to chop this guy apart, I need to supply that amount of energy. That's what bond energy means. I want to break that bond, I want to give that bond. Or when the bond forms, when naturally there's a carbon, let's say there's a carbon atom here, and there's a hydrogen atom flying by, and then they bond. When they bond, they form that covalent bond. That formation will release that much energy. That's what it means. Okay? So that's the energy needed to break, or that's the energy that will be released when the bond forms. But when I break this, so we want it to react with oxygen, O2. O2 is this, O double bond O. Then when I break this bond, right, and then we break all of this bond, leaving carbon. Carbon is going to react with the oxygen to give us carbon dioxide, for instance. So now what you have here, you have carbon now bonded with oxygen. You form new bond. Or oxygen bonded with hydrogen. The amount of energy now will differ. In the sense, earlier carbon was bonded to hydrogen. Now carbon is bonded to oxygen. Oxygen has got a different electronegativity. Means ability to attract electron. You see on the periodic table, right, as you go across the periodic table from the left to right, you're going from metal to non-metal, right? The non-metals are very strong in attracting electron. You remember we talked about it? Formation of covalent bond, which is why they always form covalent bond, or they always form the negative ion. Because they can pull electron. The one on the left, the metals are not so good at pulling electron. The ability to pull electron is known as electronegativity. Right? Electronegativity means ability to attract electron. So you see this oxygen, essentially the tug of periodic table. This guy is always so strong at pulling the electron. So I'm going to ask you a very simple question. Position of carbon is somewhere at number 4, root 4. Right? Somewhere there. And then hydrogen is far left, right? Because it's number 1. And then oxygen is on this side. Now earlier, C to H, assuming it's 450 kilojoule in order to break it. C double bond O here. Do you think I need more energy or less energy to break the double bond?
More energy.
More energy, way more. That should be around 800 or 900 kilojoule. You know why?
Double bond.
2 reasons. Double bond, very good. Second, oxygen is stronger, man, pulling the electron. It's like 2 persons holding their hand. And then I substitute one person with another person who's much stronger and tell them to hold their hand and we try to break the hand free. The stronger the bond, the harder it is to break it. That's what we call as bond energy. Energy needed to break the bond or energy released when bond is formed. So that's why the values will vary and you don't have to worry about, wow, what is the energy for what bond? Do I have to memorize it? Never. Even up to after IGCSE, even at A levels, you don't have to memorize this value because that value will be given to you in periodic table or given to you in a data booklet. In IGCSE level, that energy values will be given to you in the question, which I'll show you how shortly. Alright, so now we go back to this question and we go back to this formula. Now I've given you this. Can you guys calculate using this formula? What is the delta H for that reaction?
Wait, John, but I thought you said that energy can't be created or destroyed. So
Yes.
where is the energy coming from?
Sun. The source of the energy on this planet.
Okay. So it's just absorbing the surrounding energy?
Yes.
Yeah, okay.
50 kg.
Which is why all the old civilizations prayed to the sun. It's a source of energy. Yeah, okay guys, what's delta H? Using this formula. So total energy of product. So total energy of product, which is what? Which is 150 minus total energy of reactant, 100, isn't it? So it is 50 kilojoule.
We put
But,
negative.
but if you write this in exam, it will be wrong. You know why? Because now looking at that energy level on the left and right, I put it side by side against here. Can you tell me this is endo or exo?
Exo.
Why is it exo?
Because they're releasing energy.
Because more energy is released than energy that is absorbed. Okay, you gotta say that, huh? You cannot say because it's releasing energy. The idea is, I know what you mean, but you need to show your understanding. It's because energy released is bigger or greater than energy absorbed, correct? So if you leave your answer like this is endothermic. So you have to manually add your negative. Now why I don't recommend this formula is sometimes students forget. So I'm going to give you a different formula. Just switch this around.
Shouldn't we just take 100 minus 150?
Yeah. Which is why I'm going to flip the formula.
Is it going to be like total energy of reactant minus product?
Yes, I'm going to give that formula. So I'm going to split. This is the formula that I want you guys to use. So this is the formula that I want you to use. So we take the total energy of reactants, we minus total energy of product. That way, you don't have to worry about the sign. The sign should appear on its own. Right? So in this case, if we do it in this case, it will be 100. So delta H will be 100 minus 150. That gives us 50 kilojoule negative. So somehow mathematically it appears. Alright? So this formula is what I want you to use. This is what I want you to remember. Okay, this one. We take the reactant and we minus the product. That way the sign appears on its own. If it's positive, that means you have an endothermic reaction in your hand. Okay, so this is the formula that we will use. This formula, you never have to show it in exam. You just have to know how to use it. So the energy for reactions, the standard enthalpy is kilojoule per mole. But energy is measured in kilojoule, but per mole in the sense that when we standardize a reaction, every reaction is carried out at 1 mole in substance or in concentration. Okay, so this is what I want you to use. Yes? Yeah, sure. Alright, let me show you how this solving is done. Hang on, yeah. Okay, you guys can take a toilet break if you want, because the next round let's pause this.
You just press on it and like send.
So the next part, of course, I need you to you copy after this. Let me explain this for you. You've got to copy this into your notebook because there is no this is not provided. But this is how it comes out in exam, and you need to be able to do this. So if you copy in your notebook, you can use it to revise before exam. Okay? So now this is an example of a passive question. This is how it comes out. Now I'm going to solve this for you, and then you can copy, and I'll show you another one that you can try. Now, okay, so this is how the exam question is given. I think this is 3 marks. Yeah, this is a 3-mark question. They give us a bond amount of energy, this table of bond energy in kilojoule per mole, and then they show you that the following. They want you to use the data in the table to show the following reaction is exothermic. Now, how do we do this when we get this type of reaction? It's very simple. Now, you don't have organic knowledge yet, so I'm going to show you the traditional way. The traditional way is where we do bond breaking and we do bond formation. Okay, so it's like this, it's done like this. So the idea is all the bond before the reaction here, all the reactant, all the bond in the reaction should break. Now, before you start, you got to list the bonds. That's what you want to do. You want to list the bond and see how many is there and what's the total amount of energy. Like this, it's done like this, right? So can you guys count for me how many C to H bond exists? So we've got 1, 2, 3, 4, 5, 6. So normally I make it a point to cut it when I count in exam, just to make sure I don't miss out any bond, right? So C to H, we have got 6. So I've got 6 C to H. So what is the C to H bond value? 415. So the calculation is 415 times 6. And what is the amount? Okay, now I've worked it out already. I'll show you guys so you don't have to calculate. So we get the amount. And then next, what's the bond next? C to C. How many? 1. And what's the value of C to C? Single bond? 346. 346
that's double bond.
times 1. This is single bond.
What about the triple bond?
Is it above it? Is it triple bond or double bond?
Double bond. Double bond. Double bond. So here is a double bond. 1 C to C double bond. And what's the value? 610. So, I'm done with this, right? I've got one more here. H to H. So what is H? How many H to H I have? 1. And what's the value? 438. 436. Now this is we listing out the bond and calculating the energy. This is the bonds that are broken. So this is broken. And then we total it to find the total amount bond broken. Now all of this bond is broken and then all of this bond is formed. So then we will do the same on this side. So how many C to H? 1, 2, 3, 4, 5, 6, 7, 8. So we have C to H, we have 8 of it. So what is the C to H 415. So 415 times 8 equals to what? And then you do the same for the next C to C. So I've got C to C 1, 2. So times 2. C to C is positive 346 times 2. Then we total it up. We total all the energy here as well. We total it up in order to find the overall energy that is absorbed, overall energy that is released. And then we find our delta H, which is the energy change. Okay, so now one thing I want to remind you guys, when you do this, you have to be very, very careful. Common mistake happens, students missing out on bond, they just forget to count, or they count wrongly. Second, they refer to the table wrongly. Instead of, for instance, instead of taking 436, they end up taking 346. You want to be careful there. Alright, so wait, I've already done this for you guys, I'll just show it to you. So I've already done this. Okay, so this part is done. C to H got 6. So 6 times 415 is 2490 kilojoule. We have one C to C double bond, so 1 times 610, 610. One C to C bond, single bond, so 1 times 346, 346. One H to H bond, so times 1 only, 436. Normally times 1 in exam you don't have to show, you don't have to do it, but I'm just showing the technique. So total energy absorbed, 2490 plus 610 plus 246 plus 436, 3782 kilojoule per mole. Total energy absorbed. So total energy released here, we have got C to H 8 bonds. So 415 times 8, 2 C to C bonds, so 2 times 346. Total energy release is 4012. Exothermic or endothermic? Exo, right? Why?
Because it is greater.
More energy is released than absorbed.
Okay, so that's not a complete answer though. You got to complete it.
During bond formation.
More energy is released during bond formation
And greater.
compared to
bond.
energy absorbed during bond breaking. So that is your conclusion to this question, which is you explaining or to show that this is exothermic. Another way you can do this is you could have stopped here and write that statement that we just talked about. Or you can continue to do this. Just do this. Enthalpy change again, of course in exam no need to write the formula. You can straight away just do the calculation. So sum of reactant minus sum of product, so 3782 minus 4012 is a negative 230 kilojoule per mole. So and then you just write a simple statement. That's the final part. You just write a simple statement to say the reaction is exothermic as delta H is negative 230 kilojoule per time.
So we still need to write it.
Yes, you
Will
can.
there be a line?
You don't have to, you get space to write. I just removed it because I wanted to show you guys this. Hang on, yeah? So you don't have, it's not necessary to show this working if you want to write that statement. Or you don't have to do this part, straight away write that statement. Reaction is exothermic, energy released from bond breaking is greater than energy absorbed during bond formation. Okay, hang on, yeah? Yes, you wanted to ask, what is it?
Sure, for the reaction is exothermic as delta H, is that 2 mark?
This question.
No, I mean like for that answer, is it 2 mark?
1 mark.
So I have to add the bottom one.
Yes, that conclusion is 1 mark. So you get 1 mark for the energy absorbed, you get 1 mark for the energy released, and then you get 1 mark for the conclusion to say why is it exothermic.
Calculation is 2 marks, then 1 mark for conclusion.
Yeah, correct. So this is usually a 3 mark question. Okay, I need you guys to copy this. Yes, the question as well. So that you know this is how it's going to come out in exam. So you can use this to revise. Okay, take this one down into your notebook. Stop here. Then I record another one. Okay, alright, so some correction on the slide. So those who are watching, values have changed a little bit. Okay, so moving on to the next question. Now this is another past year question. Of course, I kind of shifted. It's the question in exam, right? It's one full page. Where this is the question, at the bottom here is this part first, and then comes this two line for conclusion. Now I'm going to let you guys try. So I want you to try. Try it in your notebook as well.
You write down questions.
Yeah, maybe if you want to summarize this like briefly, it's up to you. I leave it to you. I just want you to have this question so that when you revise for exam, it's there. Because not that many of these questions available in past years. So there's very few of this form. So I've brought, there's 3 questions. I want you to try this and I'll show you the answers. And then there's one more that is considered a little bit tough, a bit tricky. The only time where they decided to make it a little bit more tricky than usual. This is considered straightforward. Then that is my
How often does this question come out in exam?
quite often.
Then why isn't it much in past years?
In this form, not much in this form. Multiple choice, yes.
So just chlorine, right?
Okay.
What's that?
Is that chlorine?
Chlorine, yes, Cl, chlorine.
So what's the first number?
242. Positive 242.
They also cannot see you.
338. 412. 431.
Someone will six something.
The last one is 431.
431, yes.
Wait, it's 336, right? The second one? 338.
338. So positive 242. Positive 338. Positive 412 and positive 431.
This is a very long thing is for the conclusion, right?
Yes, that's the final part. I just rearranged it this way to fit the slide. In the exam, it was one long page, like the question and then those fill in the blank kind of section and then the conclusion.
So the unit is kg per mole.
Yes, correct. kg slash mole.
Oh.
So here you don't have to write the unit because they already labeled it up here. So the unit is already labeled here. So you just put the values in here.
Just so the bond's broken, right? I just write Cl to Cl, then C to H, right?
Yeah. Just write the bond here. Yes. Try this question. It's an exam question. Stupid exam question. Okay.
I don't know. Bond broken 是左边 ，bond 冲是右边，所以就想看你右边对，它 C 跟 H 有一个嘛，C 跟 C 要一个，连 H 跟 C 要一个。
The glare decreases, but the image becomes not so clear if I on the lights. Isn't it? Is it clear?
It's okay now.
Let's see, the glare is still there, doesn't help the glare.
I feel like every class got the glare. Upstairs, our old class also got.
Yeah.
Need
The projector is never meant to be shot at whiteboard.
Reflective surface.
Yeah, reflective surface.
Reflective surface.
But it's very useful to project something and write on it.
Oh yeah, teacher, one of my old schools had a smart board in the classroom. Like
Yeah.
every classroom had a smart board.
Yeah, that solves that issue.
But it's very outdated. And the markers for the smart board always
Yeah,
went
correct.
missing.
Correct.
And then
We had smart boards, but we had two here.
Yeah,
The older
the old
one.
school got.
Government
Then
school only got
spoiled. Then we wanted to repair it, but we couldn't get parts for it. It was very expensive.
Someone trying to
and the
fight.
smart board
They
also
don't push,
turn
they
into
just
whiteboard.
smash the whole board. It's like one whole.
Welcome to Asia Pacific.
They try to put punch you punch you punch you.
What's the whiteboard?
Yeah, the whiteboard is the whole thing there already.
The thing is, smart boards are very powerful. They do a lot of things. But most teachers will end up using just the basic parts of its features. As a result, we realize just normal projector, because the basic things that they end up using is the basic things that even normal projector can do.
I think the best part was that you could have like the camera on the table, then you could show like your
Ah,
then you could
yes.
just write on that paper.
Yes,
Yeah.
yes, correct.
I think when I was like in that old school, I only saw someone use the whiteboard feature of the smart board only once in 2 years. Trust me.
Okay, anyone with the answer?
It's exothermic. Okay.
What value did you get? Like your enthalpy change?
The delta change.
Delta H, yes.
I didn't count the delta.
Haven't, okay.
Or this one.
It's 115, is it?
Well done.
Yay, Audrey.
Wow, so quick.
I feel like usually like so many those pages to you. They can put the class over.
Go get it.
Or no, because it's in the class.
So the enthalpy change, because this is the same question as the earlier question that I showed you guys, where they are asking us to show that this is exothermic. So we perform the calculation and show that it is exothermic, or we write down the statement to say that the reaction is exothermic as energy released from bond formation is greater than energy absorbed during bond breaking.
Bro, I feel like I can't spell enthalpy.
This is a 4 marks question, yeah, in exam.
4 marks question. So,
Because they listed out that way, right? They wanted to give you more marks, of course.
but it's the same format.
Yeah, because the earlier question, if you notice, you can stream, you don't have to show this list. Even though you tend to do it as part of your working, but honestly, they don't mind if they don't see this. They would have given you mark for total energy for the bond broken and total energy for bond formation. So you'd have got like 1 mark here, 1 mark here, and 1 mark for conclusion. That's how it becomes the 3 marks. But here's 4 marks because they want to see values here, correct labeling of the bond and as well. Yes.
Is endothermic, right?
Huh?
Is endothermic, right?
Exo. Because the question already says it's exothermic. You just have to show it's exothermic. Okay, let's see. What did you get? This is where you have to check. Did you total up something wrong?
Endothermic is supposed to be the right side supposed to be more.
So let's see. Alright. So C to H got 4. And then CL to CL. CL to CL, only one.
Oh.
1 bond only, not 2 bond. You have 2 atoms there, but 1 bond.
Is it negative? Wait, minus 115, right?
Yes, very good, David. Okay, so check where did you. So you picked up a value. See this one. 4 times 4, 1, 2, correct? Here, it says C2H, 4, 1, 2. CL2. S1 OCL is 238. And H2CL is 41. So the sum is
Maybe an exam is better to like this because if this value is wrong, then this
Okay.
But it's possible.
if your value wrong, at least this one will be
I see your
So you're basing
I get
6.
that.
Sure.
Yes.
If we write this explanation, if our value is wrong, it will the whole thing be wrong.
You lose 1 mark.
But if you write this one, you still get 1 mark.
Safer.
But it takes
Yes.
longer time to do it.
Yeah. Safer lah, that's safer because you don't have to bother, performing. So that I recommend to students who don't remember the formula. Kind of don't remember the formula, how to get the enthalpy change. Then they just write the statement.
But if you don't know the enthalpy change, how do you do the question in the first place?
How are the marks?
They do the bond calculation, then they just see which side is greater.
Oh.
That's okay, but it's important because there are some questions that will want you to calculate the delta H, then you cannot run away from it.
How are the marks distributed? Is this for reference purposes?
Normally you get 1 mark. Let me show you guys. Okay, those who are done, there you go. Now let me show you. I want you to realize that how your answer and my answer might be different. There's something I want to tell you all, but what you have done there is correct. So C2H for total energy, C8 to CL, total energy. Do you realize your total energy and my total energy is different?
Yeah.
You
Because you didn't time.
We're recording, right?
Yeah.
Okay. Now, did you realize that when you did the way that I taught you, did you realize that bonds broken is okay because you have C2H, CL to CL? But for bonds formed, did you realize that you have 3 bonds? Which is Ca to Cl, H to Cl, and C to H, isn't it?
Yeah.
But how many space did they give?
2.
Only 2. So, where do I write the third bond? This is where, okay, now there's a difference between you solving this question as a year 10 student and you solving this question as a year 11 student at the end of your year 11 before IGCSE. Because this is the IGCSE question, right? The difference is a student who have learned this reaction as an organic chemistry reaction. You will learn this reaction. It's a reaction I'll teach you in a topic called alkane, where I'll teach you, subtopic is organic chemistry. I'll teach you that this is a substitution process. In the process, when this reaction takes place, the only bonds are broken is this and this.
Oh, yeah.
And then one Cl will go here, one H will come here. This is the new bond form, this is the new bond form. So if you notice, this CH, this CH, this CH, this CH, this CH, this CH did not change at all, was not broken, was not remade. Which is why they only left these 2. This is why there's only these 2 space left in the exam. But you know, a lot of students this particular year, didn't think about that. Despite they have learned that reaction, they still went on to solve it the way that they learned in year 10, which is you break everything. That's true. If I give you a combustion reaction, you have to break everything. Right? But in this case, no, we don't have to break anything. We only break the one that changed. And it still gives you the same answer. The answer didn't change. It still would, even though this value is the one that I calculate, the answer will still be negative 115. The answer won't change.
It will just be slower.
Just these 2 values will be different than yours, but the enthalpy change value will still remain the same.
So people got their marks minus, is it?
No, you'll still get full marks now.
So basically, you break everything,
Yes.
still get the same marks.
I don't think they would, the only thing you would have struggled, they would have, by this point they suddenly realized, hey, where do I write the third bond? And they might got a bit of panic attack and they would probably, but there was a lot of space they could have written the answer and I'm very sure they would have got full marks now anyway. Alright, but I just want you to realize this now. So, of course, at year 10 level, you guys will break everything and join everything. But when you get to year 11, when after I teach you organic chemistry and we revise for exam, I will remind this to you again. That look, you just need to break the bond that you need to break. Yes.
Actually, I thought you say if you write the answer outside the box, it's not counted.
Then cross off, then right.
Oh, you're talking about because mine is outside, is it?
No, I'm talking about
There's
the
only
box.
two spaces, so
Oh no, as long as
they
it's within
write-
the answer space, it's fine.
Oh.
In this one, right, it was almost an entire page. So the lots of empty space next to the area, like this one, right? This, in the actual exam paper, I'll show you guys. Okay, I'll show you. You can see there's actually lots of space and they know the students will do this. So there was lots of space for them to write. Let me show you, yeah? How this was when it came out. This one is 1, was it 2? Was it 2? Let me show you. Yeah, it's 2. Yeah, this is how this is the entire page. This is how it was when it came out in exam. Yeah? You see, like an entire page question.
Because I thought you said that.
Yeah, like for instance, if you write things here, of course they'll mark.
You still mark it?
Yeah, they
So
will
what's
mark
that
if
the
you-
skills?
Because in this area they will mark. For sure they will mark. If you do your working here, they will mark.
Oh.
Yeah, but an answer that's supposed to be written, like written answers, the calculation and all, they will definitely accept this area. But you know, if they only have 2 lines here, you write go 3, 4 lines down there, they won't do that, they will mark. Okay, so that's the idea. Okay, so alright, okay. Now the last question, I'm gonna give y'all, see if y'all can solve this last question. This last question is going to be a tricky one. Yeah, that's the question.
Yeah, tricky part is the size.
Oh.
That's it.
Yes.
That's
The-
it.
oh, the leg.
Because the top part, right? Okay.
Whoa.
Okay, you know what? Let me do something about it. Let me drag the thing down.
It's hard to see.
Yes, that's
Put
the
it
part.
down,
Oh.
Okay, you can see?
Oh yeah.
Better? I'll make it bigger also.
I thought
Can
you
you zoom in?
Right.
Right. Huh? Joel is in the middle. It looks like a S.
it is an S.
Solve.
Yeah. Yes.
It doesn't do it already.
Ah, yeah,
Just
yeah.
make it louder.
That's the question, that's it.
Oh, that's the question. Oh, I was waiting for.
Now I have to think how to solve this. We will. What's the next subject?
Business studies.
Sorry. It's okay one.
Anyway, let's take a little bit, maybe I'll take a 5 minutes of business study last time we skip. So, I just want you all to try this. This one you can solve straight in your calculator if you can, you can. If you want to do a rough working on a piece of paper, also can.
Oh.
But I just want to see if you all are able to solve this. Whatever you know up to this point is enough to solve this question. Okay, I'll give you a tip because actually without this tip you may not be able to solve this question. The tip is here, right? When you read this question, you know this part? The crucial part is during the reaction the amount of energy given out is 780 kilojoule. You know what this statement means? This statement is simply telling you that delta H is negative 700 kilojoule per mole. That's what that statement tells you.
Oh.
Yeah.
Is it? I don't know.
And if you don't know that, then you cannot solve it.
Is nobody copying the question or copying? That's so fast.
No. Delta H, when they say, I know when you read it, it's read it as energy given out, you think it's just the product side. No. That statement means delta H is equal to negative 780. So that's wrong.
What?
Oh,
Yeah.
so here is plus 780 of this.
When you have minus, it becomes 780. All staring from outside because they want to come inside.
Okay, so sulfur we cannot find.
Huh?
Sulfur we cannot find.
Sulfur is 0, there's no bond to break. Because there's no bond, right? It's a single atom, so 0.
Wait, I think I know how to do this.
Move forward.
Anyone with the answer? Anyone with the
I
answer?
think I know, but I feel like it's wrong.
What do you want to
Copying
find?
the question.
Those who's going to be watching the recording, please pause this. Try, then only you play and watch the solution.
Yeah,
You're probably crying at home now. Probably like 12 a.m.
Oh. Determine the bond energy together.
So you're determining the bond energy. All the earlier questions that we looked at, they gave us all the bond energy, right?
110.
And then we calculated the delta H.
110.
Wait, they want you to find the right side?
No, they want you to find one bond. They want you to find this
For what?
bond.
SF?
Yeah, let's have this one. One
Okay,
of
so
the value of 1.
275?
Right, I got it.
Answer 275?
No. 275 is wrong.
No! But there are 4 bonds, right?
Any other answer?
There's only one way, I know. Is it negative 115?
Oh, you get negative from.
Where'd you get that from?
I took negative 460 divided by 4.
Where'd you get negative 460?
I took 320 minus negative 780 and divided by 4.
Clap for him, that's your answer. Because it's delta H, which means reactant minus product, right? But here you don't know, right? Got 4 bond, isn't it? And you don't know what's the value, right? So you just make it 4x lah. Okay, each of the bond is 1x. You got 4x because we don't know what it is, right? Then here, this is 0. Here they gave you 160, so you got 320, right? So 320 minus 4x should give you negative 780.
I see.
Can you solve it to get x? Of course you can, isn't it?
Did you say positive is wrong one? You can go negative.
What?
Start creeping.
Okay, so that's the solution. So S is 0 kilojoule per mole. F to F is 2 times 160 because you have, sorry, the question is at the back. So you have 2 F to F bond. So because you have 2 F to F bond, the total energy absorbed is times 2, is 320. So hang on, yeah, let me make that question appear again. So that the students can see it clearly. Okay, alright.
Oh, yeah, this should be back right now, right?
No, 12. Yeah, but it's only right after lunch. After the after lunch, what?
Okay, so yeah, that's the working. So guys, same technique. So here S is 0, F to F is 2 times 160, so you get 320, right? That's the total energy absorbed. Then what is the total energy released? S to F, they didn't give us the information, that's what you're looking for. So I put a y here instead of an x because I'm already using an x for the multiplication. So 4y. So total energy absorbed is 4y because we don't know what y is, that's what we're looking for. Right? So enthalpy change is what? Sum of reactants minus sum of product. Which they already tell us, when I take reactant and minus product, I should get negative 780. That's what this statement means. So 780 equals to 320 minus 4y. That's the formula, isn't it? So you solve it. 780 minus 320 divided by 4, you get negative 115.
You could also take 780 divided by 4 because there's 4 bonds.
Yes. But you don't have to leave the negative part here because of course it's bond formation. But for the final answer, you don't have to leave it as negative. Because it's bond enthalpy, you can just leave it as positive. But even in the exam, you give it as negative, it's not a wrong answer. Okay? Because bond enthalpy, generally we just leave it as positive. Okay? Alright? So, why you keep disappearing? Okay. Alright? Okay. Any questions? Don't worry, I'll leave the next class we'll practice more.
Okay.
Okay, we'll look at more questions. We'll practice. Okay, yeah, can.
Want to sleep, JJ? Get on sleep.
Okay.